This is video, oh, I didn't write it down. This is video 26? Yeah, video 26. And upon reflection, I realized I need to be a little more deliberate about how we decide which groups of ones we can circle and which ones we can't circle. So I'm going to offer you this definition here. The term that's used is subcube, S-U-B-C-U-B-E. For our purposes, in a K-map, that's our context now, this being a subcube, this is 2 to the n adjacent cells, A-D-J-A-C-E-N-T. They share a side either side to side, left and right, or up and down. 2 to the n adjacent cells, where the cells are the little squares in the grid, in which each cell is beside, I'm going to put that in quotes, I'm using that as an alternative for adjacent because I've already said adjacent, in which each cell is beside in other cells. We could be beside up and down, comma, including wraparound. Wraparound is when we did that pretend, you know, where the last column is right next to the first one. We'll look at some examples like that, including wraparound. Thus, that's a good formal sounding word, isn't it, for mathematical proof or something. Thus, subcubes can be size, and I'll put a list down here, 1, because that's 2 to the 0, or 2 to the 1, or size 4. We've seen these, size 2 and size 4. 4 because that's 2 squared. I'll put those in parentheses. Maybe that'll be less confusing. Or if we've got a K-map large enough, maybe even size 8, size 16, whatever. 8 is 2 to the 3rd. There. That's a little more deliberate. How do we decide which size to use if there's more than one size? And this is going to sound kind of confusing again. We're going to have to look at examples so this makes sense. We use these sizes in increasing order, E-A-S-I-N-G, order, to cover, and that's the term that's used. I won't put that in quotes. Cover it is when you draw a circle around it, one of those weird looking multicolor circles. We use these sizes in increasing order to cover ones in the K-map that can't be covered by a larger subcube comma until all ones are covered. Holy moly. All of a sudden I'm starting to wish I had waited and written this after all the examples in sort of a summary so we could look at it and say, oh yeah, of course, I know exactly what you're talking about. Let me read this back anyway, since I've already done it. In a K-map, a subcube is 2 to the n adjacent cells, where each cell is beside in other cells. So if you've got like a group of 4, each one of those will be next to 2 other cells. If you can visualize that square that was smack in the middle of the K-map in the previous video, each one of those ones was next to 2 other ones. That's not important. The important part really is to remember we want to use size 1 to cover all the lonely ones. It can't be grouped with anybody else. The next one that we'll look at is size 2. Are there any ones that can only be paired off that are not in like a square of size 4, and so on? We use these in increasing order until all the ones are covered. Okay. I don't have room for many examples, but I'll get one going down here. And while I still got the definition on the board, and maybe we can point at it and talk about it, and then I'll have to erase it before we can do more. I'm going to zip ahead, and rather than write the original truth table, in the SOP, I'm going to say, been there, done that. We've already written it. Actually, we don't need the original SOP. That's like the big clunky Oldsmobile from 1930 or whatever. That'll always run, but it's not going to be the fastest or most efficient or anything. So I'm going to say that we've got an example that we've already looked at with logical variables ABC. Always label the columns and rows exactly the same. 0, 1, and then across the top, 0, 0, 0, 1, 1, 1, 1, 0. Why? Because it has to be in gray code order, because we want each column, each row to differ from the next one over by only 1 bit. That's how we figure out which ones they can ignore, how we can find out what they have in common. And let's say that off the truth table we found out that there's a 1 down here at the bottom left corner, 2 1s right here, and a 1 right there. Now, this illustrates, let's see, maybe a couple of these things, maybe more. I don't know. It takes several examples, actually, to cover, so to speak, this definition and description up here. I'm going to stick with pink and say that, you know what, that one. That one's on the top row all by itself. I guess I'm going to have to cover that with a subcube of size 1. Nuh-uh. It's next to another one. And that's size 2. That can be covered by a larger one. So let's see. Who is isolated? Well, this guy over here. This one's completely isolated. It's not next to anybody. Up, down, left. Oh! Also wrong. Wrap around in your mind. Wrap the whiteboard so that this is a cylinder rather than a rectangle. And you'll realize that that one is next to that one. Yikes! You know what? While that's still fresh in mind, here's how we would represent that with my dirtier pink all the time. Look at this. That's a subcube that covers those 2 1s. There are no isolated ones. There are no singletons in this. There is one of them, and while I'm at it, I'll go ahead and get rolling on the reduced sum of products over here. I might as well just leave all these markers open. RSOP. The pirate sum of products. RSOP. Okay. The pink one is what? What do they have in common? Well, they've got an A in common. A. What else? What do these 2 1s have in common? They don't have a B in common. Look at this. B is going from 0 to 1, flipping back and forth. They have a not C in common. A and not C. Let me let the ink dry on that. These 2 1s in the wraparound subcube of size 2, all this terminology you've got to keep in mind. The wraparound subcube of size 2 has A and not C in common. Because A is 1 for both of those ones, C is 0 for both of those ones, and they do not have a value of B in common. I almost closed that. I guess I could. I'm done with pink on this one at least. Blue. Let's move to blue. These 2 1s, that's a subcube. Also a subcube of size 2. Neither one of those ones is isolated. That one's easier to see, isn't it? Or at least I'll claim it is. This has got to be an OR. Either I'm seeing a 1 in the pink subcube, or I'm seeing a 1 in the blue subcube. What do these have in common? Well, they've got B and C in common. What could be simpler? B dot C. They're both on. B and C are both on for the ones in this column. Now, you might be yelling at me through YouTube land, well, what about that other subcube? You would be correct. There is another subcube. If we keep going, we could circle these 2 1s. Those are next to each other. But I'm not gonna. You know why? Because our goal was to get this thing reduced down to as small as possible, and still, where is it? Until all 1s are covered. All 1s are covered. Either a 1 is inside the blue circle or it's inside the pink circle, and nobody is left out in the cold. Here's the weird thing. I could circle this and write whatever term corresponds to that subcube, and it wouldn't be wrong. I would still get the right output, but it would not be reduced, not minimally, not as small as I could get it, because every time I put circles in there that I don't need, I'm adding more stuff over here that's moving the wrong direction. I want to stop as soon as all the 1s are covered and go no further. Okay? Let me say that again. That's an important point. I could, if you're just itching to circle that, knock yourself out. Circle it, write an additional product, and now you've got a recipe to build your circuit that's more complicated than it needs to be. That's not the direction we want to move. That's not the whole point of K-maps. K-maps are to make things smaller and simpler. What's not been covered here? Well, we still haven't seen very many examples of varying sizes, have we? 1, 2, 4, 8. Use these sizes in increasing order. I didn't see any of size 1. I did see some of size 2, and I used the ones of size 2 only as necessary until the ones are covered, and then I quit while you're ahead, and write out the corresponding reduced sum of products. Okay. That's, there'll be several examples. This is example 1. And now that all this up here is permanently committed to your memory, I'm going to get rid of it. Here's a fun game you could play. As soon as I write the K-map on the board, you could pause or stop the video and see what you get. See if you can reduce it. Maybe we haven't seen enough yet that you'd feel comfortable doing that. But after a while, that might happen. Here's example 2. I've worn out A, B, and C, so I'm going to use X, Y, and Z as the variables. I'm going to see if I can squeeze several of these, at least a couple more on the board. So I'll try to be a little more judicious, word hard for me to say, with board space. X, Y, Z, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And we looked at our handy-dandy truth table, and here they are. Yikes. We went from the sublime to the ridiculous. It looks like we're not going to be able to group any of those. We still got to write out an RSOP eventually, so I'll get that started over here to remind myself. I misspelled SOP. How feeble is that? Okay. I'll use orange this time. Are there any isolated ones that cannot possibly be grouped with another one? And you say, well, yeah, all of them fit in that category. And then you would be wrong. This one can be grouped with that one. So I don't circle this with a subcube of size 1 because it can be covered by a larger one down the road. I only cover the ones with size 1 that can't possibly be grouped with anybody else. And here we have a winner or a loser, depending on your perspective. This one can't be grouped above, to the left, to the right, not even with wraparounds. So that one, that little one all by itself. Here's something that perhaps might be counterintuitive. You would think when I'm doing the reduction that the small subcubes are going to turn into small products. Nope, nope. If every one of these ones had been isolated ones, you know what we would come up with? I know you do. We would come up with a canonical sum of products. We might have the products listed in the wrong order, depending on what order we process our circles. But if we end up with nothing but isolated ones, all circled, that means all the variable values matter. And we go back to the product that was in the original SOP. For example, this one, what does it have in common with itself? Well, X is on, whoops, I'm trying to color code here. X is on, and what else does it have in common? Y is off, not Y, and Z is on. X, not Y, Z, which is a product straight out of the canonical sum of products. We didn't get to reduce that at all. So this one's not going to shrink by an awful lot. I'm running out of different colors to use that will actually write. Let me try this one. This is hard to open. They should invent whiteboard markers that you could open with one hand. There, that's how I'll make my first million. There we go. Wrap around. And you know how to do that, don't you? Just look for what they have in common. Clearly they have a not X in common. X is off. And what else? What else we got? Y, they do not have a Y in common. Y flips back and forth between 0 and 1. They have a Z in common, but it's not Z. We still reduced it, not a huge amount, but we went from 3 different products down to 2 products, and one of those only needs a 2-way AND rather than a 3-way AND. So this was not a waste of time. It's not a waste of time anyway, even if we can't group any of them together. At least we know that we've done the best we could in trying to reduce it. So here, I reduced it down. I hope this is correct. I reduced it down to where that has to be completely represented with all three variables. This one we get to leave out y, and that looks okay. So far so good. I just can't help but ask questions. Let's do a JKL, since we haven't done that yet. Example 3. My black marker's drying out. Example 3. Start with the egg carton. I'm going to say JKL. Make it a capital L so it doesn't look like a 1. 0, 1. Then going across the top. 0, 0, 0, 1, 1, 1, 1, 0. Where are the 1s? All over the place. In the first column, that's solid 1s. The second column, that's solid 1s. And then across the bottom, fill in with 2 1s. So there are only 2 squares there that would be zeros. Now then, get to the circling. Are there any, we have to ask ourselves this every time we start one of these. Are there any ones that are isolated, singletons? They cannot possibly be grouped into a subcube with any other ones. No, that's not the case. Every one of these can be paired with at least one other one. Subcubes of size 2. Well, you know what? We could do 2 and 2 and 2 and 2 and cover up all these with subcubes of size 2. But we only do that if it can't be covered by a larger subcube. So the only place that I will circle here of 2 1s that can't be in a larger subcube is this one. Oh, I almost messed up my green marker even more than it is. It doesn't look like it, but believe it or not, that whole row, that's 4 1s. They're all next to each other. 4 is 2 to the squared, 2 to the power 2. Each one of these 1s is next door to 2 other 1s. So yeah, that fits the definition of a subcube. I would circle this entire bottom row rather than just these 2. Why? The bigger the subcube, they're called inversely proportional. The bigger the subcube, the simpler the product. The more of the variables we get to leave out. If I just circled those 2, I would see that they have a J value in common and a K value in common. If I circle all 4 of them together, look, K and L both up here, flipping back and forth like there's no tomorrow, and they're not changing anything. The reduction of this is just J all by itself, which is an odd place up there. This is variable J. That tells me, that bottom row tells me that if J is on, neither K nor L matters. So I'll go ahead and get that in my RSOP over here. RSOP starts off with plain old input J. No K, no L. No L, no L. I shouldn't do that. I'm sorry. There's an OR. There's one more subcube. These 2. Oh, I forgot to do that when I was doing 2. No, I can hear you yelling at your screen. No, these 2 are not a subcube of size 2. They're part of a subcube of size 4. You just kind of develop a knack for these over time and try not to get smaller subcubes than you actually have to use, because we want to get rid of as many variables as possible. That's what's going on here. We want to ignore as much of the input variables with our logic gates as we can. What do these have in common? They don't have a J value in common. J flips back and forth between 0 and 1. They have not K in common. I can't spell K. They have a not K in common, and L doesn't matter. Look what happened to that. These gigantic subcubes, each of size 4, and the reduced SOP boiled away to almost nothing. This, think about this. Talk about extreme reduction here. In the original, if we'd gone back to the canonical sum of products for this, we would have 1, 2, 3, 4, 5, 6 different 3-way AND gates. We'd need NOT gates on all of the inputs, and we'd need a 2-way OR gate. We'd need all of that machinery to build this using the canonical sum of products. Using the K-map reduced one, we need a NOT gate and an OR gate, and that's it. The end. It's just amazing. It is amazing. And you know what? That one got so small that I'm going to do the drawing again. Here's J. Here's K. What we got? K gets fed through a NOT gate. J is straight up. And they go into an OR gate. Done and done. And the output is whatever function this logical function was. That's all we need. That's all we need to implement this. Compare that to all the AND gates and OR gates and the NOTs and everything you would need if you had used the canonical sum of products. Okay. Look at this. I'm going to wrap around. It doesn't look like it, but this section down here is actually, no, that is next one below. Okay, so much for that. I wrapped around earlier. Example 1, when I went off the bottom, it wrapped around and went up to example. Okay, enough of that. Sorry. These things just pop into my mind, and sometimes I don't have the willpower and self-discipline to hold them to myself. Ooh, that was JKL. Let's get extreme. It's always fun to get extreme, isn't it? Example 4. What could extreme possibly mean in this context? You might be shuddering in fear now. I can call this XYZ, whatever. And I'm not even going to bother to label this. Here's extreme. What if it's solid ones all the way? Well, for one thing, we'd end up with one gigantic subcube. That is a subcube. It's size 8. They're not any individual ones. They're not any ones that can only be paired with another one. They're not even any ones that could only be in a subcube of size 4. They all go into one subcube of size 8. What does that mean? It means they have all values of all variables in common and none of them matter. In terms of implementation, there's actually a special symbol in the digital logic simulator that looks like this. An upside down triangle with a 1 permanent power. Our permanent power, if we're implementing this as a logic circuit, is kind of weird. Our permanent power, I keep saying that over and over because I've gotten it right every time, would power our light bulb, and the light bulb would permanently be on. That's a neat little picture, huh? I implemented that circuit. No ands or ors or nots needed. We just connect it to the power source and the light bulb stays on for this logical function. Now I'm going to do the wraparound. I can't even read that. That was an XYZ. For the extreme example. Example 5. You know what? It takes a lot of examples to get a feel for this. That's why I'm so happy you're still with us and watching all of these intently, writing them down and thinking deep thoughts as you write. I'm going to use ABC for example 5. And this one will also be extreme. Let's see. ABC. And the ones. Oh, I didn't write the RSOP. I'm sorry. RSOP equals 1. No variables involved. Permanently on light bulb. Now then, this one. Let's also do extreme. And the ones, oh, no ones. It's completely blank. It could happen. That's a legitimate truth table, nothing but zeros. This truth table had nothing but ones in the output column. Let's say we've got one nothing but zeros. I'll start by writing the RSOP. RSOP equals 0. You can't turn me on, well, no matter what you do. I'm permanently off. A permanently darkened light bulb. There's a special symbol for that. It's kind of like an upside, well, it's not an upside down triangle, but it's a triangle that we connect to from the top. It looks like a triangle made of little lines like that. It's called the ground. We would connect the ground to our light bulb. Connect the light bulb to the ground. And that little stuff there, that means the light bulb's on. I'm not putting anything inside that. That means the light bulb's off. And I could label these. I probably should. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. There. Example 5. I think I've even got some more examples here. You know what? I'll save some of the fun for you. You can make up your own and try these out. And if you're not sure, you can send them to me. Or let me see if I can cook up a little short order cook here, cook up a lab where you get to try some of these, and then I'll take a look at them for sure and see if you've been doing this correctly. But for now, I'm going to stop right there and say see you online.